You, Michael? So we started talking about chemotaxes and these PKS equations for Patlock, Keller, and Siegel written here. And I said at the very end, count the number of parameters in this problem. Okay, so let's count. There's the diffusivity, the mobility, 2, the length scale, 3, gamma and beta, 5, and then epsilon, the 6 parameters. So guess what? If you vary these parameters, you can get all kinds of different behavior. You can get this kind of tame coarsening behavior for some of them. And you can get very interesting just collapse to points for other values of, ranges of values of these parameters. And there are hundreds of papers now that have been written about the system. Generally, they let epsilon be 0. Okay, and when epsilon is 0, then something non-local happens. Okay, so if we let epsilon equals 0, gamma equals 1, and also beta equals 1, okay, we have left d and mu and alpha. Okay, then this implies that 0 is alpha squared Laplacian c minus c plus n. Okay, so c is equal to 1 minus alpha squared Laplacian all inverse acting on n, which is this kernel, the Green's function for the Helmholtz operator acting on n. So this convolution represents taking the inverse of the Helmholtz operator, okay, solving the sort of Helmholtz-Poisson equation. Okay, and we call this thing, this k star n, we can just call it in bar because it's a smooth version. C is a smooth version. This is smoothing of n. This is smoothing because if we looked at C hat of k, this would be equal to 1 over 1 plus alpha squared k squared n hat. Okay. So you give me an n, I take its Fourier transform, I smooth it, I invert the Fourier transform, I get C. Okay, it's a smoothing because it's reducing the high wave numbers. There are wave numbers that are high, for which k alpha is greater than 1, and wave numbers that are low, for which k alpha is less than 1. That's where this length scale alpha comes into play. Okay, it determines which wave numbers in the solution are going to be playing a role. Okay, so what I want to do is make some kind of argument here about when there's a collapse, what causes the collapse? And what kind of a collapse is it? And what are the conditions for the collapse to occur? Okay, so let me rewrite this thing as d by dt of n of x and t equals minus the divergence. Let me first write it as so we can see the balance. So it's the divergence of d grad n minus the divergence mu in grad in bar. I'll write it one more time as K star in. Okay, so this is diffusion. And this is the traction. See the minus sign? And the evolution of n is driven by a balance between diffusion and attraction. If the attraction were to take us to a delta function, or spikes of some kind that would be growing, the competition would be, can the spikes grow faster than diffusion can burn off the tips? Okay, if it can, boom, you get this chemotactic collapse. Okay, so now to get what this attraction actually does and, fix the game so that the collapse occurs, we're just going to set d equal to 0. Okay, so now we're down to two parameters, mu and alpha. Okay, so d by dt of n, x and t, now is going to be equal to minus div mu in grad in bar, which is equal to minus div mu in grad df dn for f integral of 1/2 integral in k star n dnx, but we can just think about it as dnx is 1/2 integral of n in bar, so that delta f delta n is in bar, right? K is an even operator. So you take variations with respect to n, you get two k star n's, which cancels the two, right? So that df dn is in bar. That's where the gradient comes in. So this is the variational equation, the same type as Cahn-Hilliard, but now it's a non-local Cahn-Hilliard equation. Okay, because n bar is not the average over the domain. It's the average convolution that's falling off exponentially in both directions. Okay, so it's a blob. Okay. I want to say, yeah, I want to write. Well, do I want to write? Yeah, I want to write one more thing. I want to introduce a velocity. So this is something like a Darcy velocity. I'm going to call this thing div of n times u of n. Okay, so it looks like a continuity equation with a velocity un, and un is mu grad in bar. Okay, so this guy's actually functional. Well, it's a functional of n, so let's just leave it as it is. Okay. So what I claim is that this equation produces singular solution. So this equation produces singular solutions, and this is blow up in finite This is where PDE theory usually stops. Blow up in finite time. It's a bad model. But we actually would like to see this. We have no regret for blow up in finite time. And let's use it as an opportunity to see how these singularities interact. Okay, so the question is, does this equation have singular solutions? Okay, so I'll show you the singular solutions as an ansatz, and then I'll show you the numerical simulation of the approach to these singular solutions. Okay, so here's the ansatz for the singular solutions. So you let n of x and t be equal to a sum from a equals 1 to n of some weights. Let's do it in one dimension. W sub a of t delta of x minus q a of t. And in bar of x and t, because you need that, you have to take its gradient, is the sum from a equals 1 to n w a of t times k of x and qa. Right? We integrate this guy, right? So he's k star n. Everybody know what k star means? Yeah? Okay. I'm going to assume you know. It's convolution with the Green's function, or the kernel, k. Okay, so we have n and n bar. And the issue is, if we substitute these into this equation, what do we get? Okay, if we get Butkus, nothing is consistent, it's not a solution. But if we just get dynamics for these quantities, WA, the weight, and QA, the position of the delta function, okay, then this is a solution for these equations. And when we substitute it in, we get WA dot of t is 0. This always happens when you put this, this sort of substitution into a continuity equation. The weight is preserved. And the total weight, right, as you knew. Okay, so, but each individual weight is preserved. And Q dot of A, is mu grad in bar evaluated at QA, T, and T. I'm going to call that U of QA, T, and T. So it says that N is the sum over weights WA times a set of delta functions, points on the line where the delta function lives, that are moving around at positions QA of t at a velocity which is the Darcy velocity. Okay, it's that U. This U here. Oh, it's pretty simple, right? So these, if I have delta functions as my ansatz, then I get a consistent set of equations. And if you take A equals 1 and 2, you can substitute in for n bar, right? It goes in here. And take the gradient of that, and you will get the interaction between the two particles. Okay? or you can cheat and just look at the numerics. So let me show you what that looks like. The issue is we're looking for singularity. Okay, I'm going to plot n bar as a function of space and time. And if n goes like a delta function, then n bar goes like the Green's function. And the Green's function for the Helmholtz operator is 1/2 e to the minus the absolute value of x divided by alpha. Okay, which looks like this. So if n is a delta function, has a peak there where there's a jump in derivative, right? Exponential coming in both ways, absolute value. So if we see this shape, then when we plot n bar, then that corresponds to a delta function in n. So we're looking to plot n bar as an initial value problem. And this is how it looks. Okay, so this is a smooth initial condition. Okay, this is called a waterfall plot, where at each successive plot is at a delta t time step greater than the initial time. Okay, and you see, well, it's kind of a gentle Gaussian actually, and as time goes on, it steepens at the maximum, and then what's happening is that there is flow in like this to the region which is getting taller, but it's a continuity equation. So when there's some kind of material that's flowing in, and when it flows in, it reduces, it produces the minimum, okay, because things are flowing in. But that gives another maximum, and so another maximum gets created. Let's see, and another one, and these are the other guys on the other side because this is symmetric. And so this guy here gets created by that maximum. This guy here runs into it, this guy runs into it, and it gets taller, and the total weight is conserved. So the weights of these guys, when they run into each other, two of them just clump together, and their weights add. Okay, and as time goes on, the interactions keep adding until at long times there can be only one. Okay, so it's a delta function whose weight is the sum of all the weights. Okay, so here you see it with n bar, the development of the singularity in the Keller-Siegel system when the diffusion is 0. And you turn the diffusion on, and then there's a balance. Can the diffusion act to slow down the blow up or not? Okay. So let me show you that the blow up actually occurs as a result of this. This blow up actually occurs as a result of the maxima. But first I'm going to write an exercise. Okay. So the exercise is show. Oh, this is Cambridge, so it's called shoe. That the PKS with d equals 0 admits delta function solutions in any dimension. So what we do in 1D is correspond in 2D to just cutting along through a 2D solution. The 2D solution, we'll look at some examples of how you write the solution. Would be a curve. So it would be blow up occurring on a curve. Okay, so let me. Okay, what you see here on this graph in the inset is 1 over the maximum value of rho in the domain as a function of time. It's 1 over. And here it's small, and there it's big, and so 1 over that is big and then small. And what you see is that rho max is increasing, so 1 over rho max is falling, just kind of naturally falling until it gets to a certain time, and then it just boom, gets large as rho max. It blows up. So at subsequent times, this is numerics, and so at subsequent times, rho max is always large. And that corresponds to this behavior. Okay.
In the simulation plot, it looks like rho max would decrease like there would be some kind of jump when the side mass.
Oh yeah, I see. Right. And why is it so regular?
Yeah, exactly.
I don't know. That's what this simulation showed. I see the jumps, and I just don't see them in 1 over rho max. Sorry. Maybe there's something incorrect about the plot, because it looks like it's just kind of at each time step not taking much of a jump. I agree. I don't know.
So if you start with symmetric initial data as you have, and you converge to a single plant physical stationary asymptotically,
What?
it looks as though QA goes to a constant.
QA goes to constant.
Is that always true with symmetric initial data? Is that clear?
QA, it looks like QA goes to a constant, right? Because the various Q's interact with each other. Yeah, so okay, if you're in a plane, when you think about these solutions, you get a delta function solutions. What they do is they move toward their center of mass all the time. So it's just like it's supposed to be describing cell movement, where the cell moves up the gradient of this concentration, and the cells themselves secrete this concentration. Okay, so as you know, and they secrete as they move, and so the other nearby cells keep moving toward the center of mass. And so eventually, and when they run into each other, they clump. Until the end, there's only one, and it's symmetric. You know, it moves along in one dimension that way. Okay. Okay, so we consider 1D PKS with d equals 0. And you can think of other questions to ask, I guess, looking at these PDEs. And so there's a paper by Horstman which has hundreds of references to analysis of Keller-Siegel. And it's usually about blow-up. Okay, so we consider this, so no linear diffusion and screening kernel k alpha is e to the minus mod x over alpha, and n bar is the convolution of n with k.
Do it.
I have a question. Why can you set d equal to 0?
That's what I was thinking of when I said there were these mathematical questions. I'm not setting it to 0. I'm actually just looking at what one term does. Okay, and one term causes blow up, and I know what the other term does. It causes diffusion, and so we're just studying the effect of the other term. If you take d equal to 0, and that's what approaching 0, that's what I was referring to as other mathematical questions. Okay. Okay.
So you are not claiming you're solving the complete problem. You're
No, I'm solving a part of the problem that has no linear diffusion. Okay. You see, remember, there are hundreds of papers written about this system, and this is just, and each one of them solves part of the problem. Right. Okay, so here's our equation. Well, we know our equation. Here's a theorem. Call this an anti-maximum theorem. Okay, so we know for diffusion we have a maximum theorem that the solution cannot, with time, cannot exceed its maximum at the initial time. Here, with this other piece, we have anti-maximum theorem, okay, which says if n has a maximum some n m for max that exceeds the domain average of n bar, or n in brackets, then nm as a function, the value of the maxima as a function of time must diverge in finite time. Okay, so this is our theorem. We're going to prove this theorem. So it's supposed to be explaining why maxima here produce the singularities. Questions?
I have a small observation. So I mean, one thing, you might sort of try to think naively about this equation is if n bar were just n, then it's the porous medium equation.
Yeah.
But then it doesn't work. So the n bar, the convolution,
It's crucial.
is crucial.
Yeah, it's crucial. Non-locality. Remember I said there are two ideas. Non-locality and Lie derivative. We haven't come to Lie derivative yet. But non-locality apparently can completely change the solution and allow singular solutions. And that's what I'm interested in, is the emergent singular solutions from smooth initial conditions.
How this approximation by data functions depends on alpha. I suppose it works only for sufficiently small alpha.
It works for what?
Such kind of approximation by delta function solutions, it works probably only for sufficiently small alpha or for whole range of alphas.
Sufficiently small alpha? No. You see these widths here of the exponential, their width is alpha, right? The delta function is immaterial because this width is obtained by taking a convolution with the kernel. Okay, that's what we're plotting. We're not plotting the development of delta functions, we're plotting the development of the Green's function of the Helmholtzian. Okay, so to prove this theorem, I'm going to begin with a lemma, which is basically exactly what I just said a second ago. K alpha equals 1/2 e to the minus x of alpha satisfies 1 minus d by dx squared of k alpha x equals delta function of x. Okay? So proof, you can do proof many ways. One is by saying, here's my operator, I construct my Green's function by variation of constants. But another proof is just direct calculation. Okay, if you operate with this guy on this guy, one of the derivatives will bring you down an absolute value, a signum, and the other one, the other next derivative will give you a delta, and everything else will cancel. And so this is a standard result. And now, proof of the anti-max theorem. Okay. So the idea of the proof is to show that if your maximum is sufficiently high, then it will go to infinity in finite time, the maximum of n. Okay? So, look at the motion of n sub m of t. Okay, it's governed by d by dx of n d by dx in bar, which is equal to n sub x in bar sub x plus n in bar sub x. Right? And we evaluate this at the maximum, okay, for which that guy is 0. Okay, we'll have only this one left. But, well, let's put it beside it. N bar sub xx is equal to n minus n bar over alpha squared. Right? Because n bar is the Helmholtz operator acting, and the inverse of it acting on n. So n minus n bar is the rest of the Helmholtz operator acting on n bar. Okay. Then the equation says d by dt of nm of t dt is equal to nm over alpha squared times n minus n bar at position xm Okay, and in bar, so I have my signs right. Yeah, right. In bar is less than the average. Let me see how to say this. Well, to put it another way. Yeah, in bar is less than an average because the average averages over 1, and in bar is averaging over things that fall off and is smaller than 1. So this guy is greater than or equal to nm over alpha squared times n minus the average of n. Right. Okay, and so this implies that nm goes like alpha squared over t0 minus t as soon as nm gets bigger any place than the average. Okay? So n, the maximum, blows up in finite time, and that's creating these delta functions. We know that it goes to some solution, and we know that the delta functions are a solution. Questions?
So one small comment. So when you started doing this and you wiped out the linear term, I was expecting to see a Riccati equation. Sure enough,
There it is.
I mean, this complicated looking thing, and so all it is the ndt equals n squared.
Yeah. Yeah, at the maximum. Yeah. Okay. So yes. Yeah, let's see. So there are another set of states, okay, that occur not when when mobility is mu times n, but if the mobility is a constant times 1 minus n, then as n goes to 1, and everything stops. Okay, so that's these states coming together, jamming together, that when you have a mobility which is decreasing with the density, then you get states which start from some Gaussian shape. Well, this is not seen very well here. So it starts from some Gaussian shape, the pink one, the blue one, and it steepens, goes to a flat equal to 1, okay, with a thickness in the decrease to 0 like gamma. Okay, so these are so mobility before we let mobility increase within. If mobility decreases to 0, if mobility is 0, things stop moving, and that means they're jammed together. They can't move. Okay. I was going to give you an exercise, but I'll just tell you the exercise. See, here we have n is a set of weights with delta function support. Okay, so write the pKs equation when there's more than one type. More than, so that there's more than one species, n sub 1, n sub 2, and so forth, interacting with their reactants and with each other. Okay? That's an interesting problem. Another problem, which is much tougher than the Cahn-Hilliard coupled to a flow, would be to couple the pKs equation to the Navier-Stokes equations. That should be interesting too. We should see, we saw those patterns, and we would see them mix up just as before, like for Cahn-Hilliard. But if you have blow up going on, then what does it do? Okay. Yeah. Andy warned me about this. It's not the wrong size. I mean, it's not the right size. It's the wrong size. Yeah. Yeah, okay. I'll do the same as before. I'm going to introduce magnetization models. So I'm going to introduce some magnetization models that have the same properties, but more dimensions than what we've been looking at. So I'll motivate this equation a little bit later. But so we have some magnetization density is a vector m in 3 dimensions. And we have a scalar density psi. They satisfy an interesting equation. d by dt of psi is the divergence of psi times v. Okay, continuity equation, as you'd expect. And next time I'll tell you why you expect this stuff too. Okay, and the other equation is d by dt of m is equal to divergence of m v, each component of m. So far, so good. Okay, we don't know yet what v is, but we can handle this. Except magnetization interacts with itself this way. So it's a vector, and it has this additional vector interaction that comes because each of the particles is carrying along a little magnetic element. These are magnetized material. Okay, so this is the new bit, and we'll discuss that. And v is mu psi d by dx of dE, of delta E, delta psi, plus mu m vector dot d by dx of delta E, delta m. So I'll stop here, but show you the corresponding simulation for magnetic materials. Okay, and this is how it looks. So starting from a few initial conditions at some frequency, you can see these things growing up, colliding, and this one here is somehow not symmetric, and it comes across. This one is magnetic field, and this is psi. So you see these equations have one simplifying redeeming feature, and it has to be true if you want to have a particle interpretation of this thing, is that the psi is carried by velocity v, and so is m. Okay, these are particles that are moving along. They have properties psi and m, and so psi and m have to move together at the same velocity. Thanks.
You didn't tell us, so
maybe it's an exercise, but when you switch that diffusion term back on, I presume that limits the blow up, so you still see the initial tendency, but it perhaps
Now, if the thing is, you put the diffusion on again, then for some values of the parameter, there's still blow up, and for others, there's not. And it's a big mystery to get to understanding the blow up, let alone how they interact after they blow up. So the answer is diffusion will not burn off all of the spikes all the time.
Well, but do they still go all the way to infinity then?
Yeah, still blow up in finite time. Yeah. This a lot of times I say to people, "Oh, I'm thinking about working on the Keller-Siegel model," and they say, "No, don't do it. Don't." So many people, and they say things like, "Don't you see going up the path to Keller-Siegel the bones of the people who went before you?" And they didn't even go very far. So I'm just looking for using Keller-Siegel to motivate why non-locality produces delta functions.
Okay, one other question? Actually, let me ask you about the magnetization equations, because you've got pictures in one space dimension, but you've got divergence there. Are we missing something, or are they all d by dx?
These are one-dimensional in one dimension,
Okay.
but they can be any number of dimensions.
So then your expression for v
This
plus
equation
gradient
here-
is gradient. Okay, yeah. I told you. It was
Well, actually, when I was writing it, I was writing d by dx underlined. D by dx underlined. And as I was writing it, I said to myself, I don't need to write that. It's only going to cause confusion.
Let's thank Darrell again.